Great. So let's go ahead and start talking about C++. Thanks, Will. We'll see you soon. So C++ was developed a long time ago. It's kind of hard to believe how long ago it was. In fact, it was developed probably before most of you were born, which is kind of scary. It was started in the early 80s by a guy named Bjorn Strustrup, who then was a researcher at AT&T Bell Labs. And he wanted to be able to write software for larger scale systems while still being able to preserve a lot of the efficiencies that people have come to expect with languages like C. So C has lots of great characteristics. We'll talk about a few of them. It's very efficient, takes good use of resources on the computer, but unfortunately it's a little bit lacking in certain features that make it easy to write big programs. So his goal at the time was to write extensions, add extensions to C called C++ that would make it easier for people to build bigger systems. And the original C++ language processing environment was called CFront, and it actually took C++ code and generated C code, and then you would compile that with your favorite C compiler. I started using C++ in 1987 or so I've been doing it for quite a long time, over, gosh, 25 years at this point. And it's really progressed a long way since then. Compilers are way better. People actually generate native code, not C code anymore, and by and large, and so it's a much better environment. C++ builds a lot of things on top of C. Now, here's the funny part. When I first started teaching this kind of stuff, which was a long time ago, people in those days were C programmers, and so to teach them about C++, you had to sort of say, well, you know this about C, and so C++ adds these new things. Nowadays, almost everybody who's starting to learn to program C++ comes from a different background, most probably a Java background. In fact, you guys probably learned Java before you learned C. So some of the things I'm about to say are a little bit funny because they're in comparison with C, and if you're familiar with Java, a lot of the C++ stuff looks very similar because the syntax is almost identical. Although you'll see there's a bunch of places where the semantics are quite different, and that can be a little bit confusing. The good news is if you know Java, which hopefully all of you do, learning C++ is pretty straightforward. The main issue is the fact that you have to manage memory more explicitly, and there's these crazy things called pointers that are out to do you harm at every possible turn. So you'll get more experience with that if you haven't already got that experience. But the main thing that C++ added to C was it added better support for type safety. C can kind of let you do some crazy things. C++ makes it really hard to do crazy things that are bad. Then it also added support for classes, which were ways of being able to abstract from certain properties. We'll talk a lot more about those. It also added support for so-called object-oriented features, which we'll talk more about, which allows you to extend existing things without breaking what you've already got to make it easier to add new capabilities or enhance what you've got while not throwing away what you've already written. And then it also, more later, added other capabilities, things like generic programming, which are templates or parameterized types, which give you a way of abstracting over the type system, which is pretty cool. And then more recently, it's added a lot of support for sort of functional programming in various ways, like lambda expressions and a lot of the types of things you'll see in the C++ standard template library. So it's got a lot of different pieces to it. It's kind of funny, if you go back and look at the first book that Strustrup wrote, it's not very big. It's probably several hundred pages long. And now you look at the fourth edition, and it's like 1,000 or 1,200 pages long. So it's got a lot thicker. Ironically, as C++ has evolved and they've added more features to it, it's actually gotten somewhat easier to use because a lot of the weird quirks that occurred in earlier versions of the language because of non-consistent behavior between language features, most of which were inherited from its C heritage, are fixed now. So things are actually a lot more consistent and easy to understand in many ways. And we'll talk more about that as we go along. If you look at C++, you'll sometimes be confounded by some of the design choices that were made. There's certain things that Java programmers or C# programmers or Python programmers or programmers accustomed to writing so-called managed code find very perplexing with C++. Manual memory management being one example, pointers being another example. In almost every case where there's some perplexing, confounding feature of C++ that doesn't seem to make a lot of sense, for those of you or those of us who have experience with these more managed languages, you'll discover the reason is for runtime performance. It's to make sure that when you write C++ code, if you know what you're doing and you have a good compiler, you can write code that's very, very efficient from the computer point of view. It runs efficiently on the hardware that we have today. that's been an important property for most of the time of computing. In the last decade or so, hardware in many environments is getting fast enough that we don't tend to worry as much about performance in terms of size, weight, power, etc., as we used to. So nowadays, modern smartphones written in Java, written in C#, written in Objective-C, those are languages which are not as efficiency focused or obsessed as C++ or C, and it still works pretty well. What's interesting, though, is if you start looking under the covers in those environments, you start taking a look, for example, at iOS, you take a closer look at Android, you'll actually find that a lot of the code that's the systems code, the code that's there to make it run efficiently, is actually written in C and C++. So people will oftentimes have a C and C++ engine with some Java veneer thrown over top of it to make it easier to program from an application point of view, but there are places and times and domains and so on where efficiency still really makes a difference. So the systems part of these mobile platforms, the server-side aspects, often very, very important. So there's a time and a place, and C++ is extremely well suited for that type of an environment. There's a lot of stuff that's actually not part of C++ that you might find in other languages. So you don't find, for example, support for, let's say persistence, garbage collection, or distribution in C++. So those language features, which you might find some of those in other languages, you don't find them in C++. Until very recently, until C++ 11, you didn't find concurrency or synchronization as part of C++ either. We'll talk more about this in a second. So the goal was to keep it as lightweight as possible to make it easier for people to write compilers that would be very efficient for the hardware in which they were trying to run. Some other goals that were very important with C++. Backward compatibility with C. They wanted to be able to take existing C libraries, existing C ways of doing things, and make them work pretty much without change in C++ programs. And by and large, that's worked out fairly well. There are a few little minor things that sometimes change, but you can pretty much take C libraries that exist already, things like various windowing toolkits or system call libraries, system libraries, the standard C library, the Unix API, the Windows API, other kinds of things, and encapsulate them easily to use with C++. They also work with conventional build tools like Make, which you'll get a chance to use in this class, the Make development environment, which is a way of ensuring consistency between source code and object code to keep things from getting out of sync. Another design goal was to try to make C++ as close to C but no closer. What that meant really was to make something where a C programmer who was familiar with C would have no problem learning C++, but they didn't want to take all the weird quirks of C and make that part of C++, because that makes it easier to write programs that don't work properly. And that's becoming more and more important. If you haven't noticed, in recent years, people are really starting to take program safety, program reliability, software safety, software assurance a lot more seriously than they have before, because the consequences are so much more catastrophic if they get it wrong. A couple examples come to mind. So anybody here ever hear of the Toyota unintended accelerator problem? Right, so still not entirely clear what is going on there, despite a lot of lawsuits and a lot of smart people looking at that code. There's some reasons for that. They wrote it sort of in assembly code, so it's low level and horrible. But they think it has to do with defects in the software. And so that's a good example of software being incorrect or unreliable having literal impact on human life. That's one example. Other examples, you probably see a lot of stuff in the news these days, things like massive data breaches. It seems like every week now there's another company that gets hacked. Target was a recent one. Lots and lots of websites. People lose important data. Sony had some problems a couple years ago with their gaming systems. It's a big issue, right? People are getting their identities stolen. It's a big hassle for the retailers and so on. So that's a big thing. Goes without saying, anybody who's paid attention to the news over the past couple of months, the healthcare.gov fiasco, all these things are software related. It's because people really don't have a good handle on how to write code well. So writing things with better languages, using better tools, using better methods, using better patterns, frameworks, etc., all those things taken together can make a real difference. And so that's something that's important. some of the things that you'll find in C++, because of its focus on performance, tend to conflict with what we would consider modern software engineering practices. By the way, if you can't read this, it says, it's Bill Gates standing in front of the blue screen of death, and it says, if he had a nickel for every time Windows crashes, it says, oh wait, never mind. So obviously he has lots of nickels. I think he's now the world's richest man again. I don't know how this keeps going. I guess the stock price goes up. Even though he's trying to give away all his money, it's hard when the stock price keeps going up. So some of the things that make it hard: compiler optimization. C++, even though I said it's very efficient, it tends to allow people to write code that gets really close down to what the underlying machine is doing with respect to memory addresses and so on. And a lot of those kinds of low-level programming techniques make it very hard for compiler optimizers to optimize certain parts of the code. So when you start doing things like taking the address of memory, taking the address of variables and so on, it gets really tricky for the compiler to figure out what's going on. And so that's one thing. Modern languages give the compiler writers more opportunity to optimize the code. Another issue is sort of separate compilation. One thing you can do in C and C++ is you can write your code in separate modules, .o files as they're typically called, or .obj files, or different kinds of libraries, shared libraries, DLLs, and so on. And then you can take a bunch of those things and you can link them together to form a complete executable. It's important in terms of understanding how computer software all integrates together to make applications and services and so on. And the long and the short of it is this separate compilation feature is very useful, but it makes it difficult again for compilers to do optimization that cuts across those different module boundaries. And then of course another issue is that the use of dynamic memory management is very error prone. And if you have never had the wonderful experience of segmentation faults or bus errors or other strange glitches you get when you run your program, you probably will when you take this class. By the way, does anybody know the best way to address the challenge of dynamic memory management in C++, other than use Java, which is not the right answer in this class? Does anybody know what the right thing to do is? So you'll learn this, and I guarantee it'll save you a lot of time. Learning to use something called valgrind on Linux. There's other tools like Purify and Bounce Checker and so on other platforms. And if you're using Linux, which you'll have to do, valgrind is your friend. That should be part of the virtual machine image that we were just talking about that you should all have as part of this class. So valgrind is a tool that checks to see whether or not your program is violating the memory rules of C++ and C, and it instruments your binary, and then as it runs, it checks to see whether you're doing silly things, and if you're doing silly things, it'll tell you what you're doing that's silly, like you're indexing off the end of an array, or you're double deleting a pointer, or you're trying to write memory to data, you're trying to write to a memory segment you never allocated in the first place, and so on and so forth. So there's lots of these kinds of problems. I guarantee you when you start writing the more complicated parts of the solution, which might even be the first program depending on how much background you have, you will find it incredibly useful to run valgrind. And that again is something you should get in the habit of doing, because if you have those kinds of errors in your code, you get lots of points taken off. So real simple way to solve that is just to get accustomed to using the tools. Here's a high-level view of C++. This gives you sort of a broad language-centric perspective. So everything that's in the light blue part are sort of C++ stuff. Everything that's kind of outside of the light blue part are things that are from the ecosystem. So if you were a C++ developer working on a commercial project, you would have access to these other things. They might not be part of the C++ language, but you would still have access to them. We'll ignore them for the time being. So here are the main things. One thing you notice that part of C++ is the C standard library and all the C features. So pretty much everything that's in C is also in C++ with a few very minor issues that you'll probably never run across unless you have to maintain legacy C code. So that's already there. But much more interesting are things called classes. You should be familiar with those at this point. Templates, you probably have a little bit of exposure to that. You'll get a lot more in this class. Overloading of operators and functions, we'll do a little bit of that. A little bit goes a long way. You have to be careful with that. This turns out to be primarily useful for what we're going to be doing when we deal with iterators. And you'll deal with iterators when we start doing C++ standard template library. Then there's a lot of other stuff in here. Exceptions, we'll spend a lot of time on that because it's not very well understood. Other things, references, namespaces, da-da-da-da. So those are some of the key things you have in C++. And I'll boil it down. There's literally hundreds of features in C++, not all of which are important to understand at the beginning. But the language is just part of it. It's not the whole piece. There's also a lot more that you have to learn about to be an effective C++ developer. And one of the key things is the standard library. Now, the C library comes along for the ride. So if you have a C++ compiler, by the way, it's almost impossible to buy a C compiler today. Almost everybody sells C++ and C compilers together. But if you get a C++ compiler, there's a C library lurking in there somewhere. Use it sparingly. It doesn't really give you what you want, and pretty much everything that it has, C++ has a better way of doing with some of the other stuff we're going to talk about. There's a bunch of things in the C++ standard library. There's a string class that's very useful. There's a threading class that's new with C++ 11. There's ways of reading data in and out of the system called I/O streams. But the biggest and most important thing is the standard template library, which is a subset of the C++ standard library. So if you take a look and zoom into STL, here are some of the key things you'll find there. There are 4 or 5 main abstractions, depends on what you consider to be a main abstraction. The main abstractions are containers, which are basically data structures like stacks or maps or vectors and so on. You probably got some exposure to those, hopefully in 201 with things like stacks and abstract data types. Then there's also these things called algorithms. Algorithms work on containers to do various things. They manipulate the contents of the containers, they access the contents of the containers, and so on and so forth. There's algorithms for lots of different things. There's sorting and searching algorithms. There's so-called mutating algorithms. There's non-mutating algorithms. You get exposure to a bunch of those things pretty quickly in the next couple weeks. Then there's also something called iterators. Algorithms don't access the contents of containers directly, but always through iterators. And iterators are very important in STL. They're a pattern. The iterator pattern is a pattern in the textbook, the Gang of 4 book as it's called. And they basically allow you to take a look at each element in a container or a collection one at a time in some particular order. In STL, you can do it in forward order or in reverse order. When we get later on in our class here and we start building an expression tree example, you'll see how you can write iterators that traverse containers in all kinds of different orders. Level order, post order, pre-order, in order, and so on and so forth. So those are the big 3, containers, algorithms, and iterators. And then depending on how you look at it, there's also these things called functors or function objects, which are basically the strategy pattern. We'll talk about that later in the class. And they allow you to customize the behavior of containers and algorithms. So a simple example would be the sort algorithm. By default, sort sorts things in ascending order. But if you pass in a function object, also known as a functor, you can get it to sort things in the other way, in descending order. So that's an example of that. Lots and lots of other examples.
What sort of form would that functor take? Would it be like a string saying you want to reverse? Or
no, that's a good question. So the question was, how do you express functors? The great thing with C++ is everything's classes and objects. So what you do is you simply, mostly when you have functors, you have an anonymous object of some predefined class, which is going to be some kind of function adapter or functor class. So in that case, in the case of sort, you would use either std standard : greater, which sorts in descending order, or less, which sorts in ascending order.
Why would you use that? Why would you use that instead of overloading the function to say, like I said, make it have a greater argument, for example?
You could actually use a function in that particular case, but it has to do with the whole generic programming concept in STL, and it's an idiomatic type of thing. Nowadays, you can also often use lambda expressions in cases where functors used to be used as anonymous objects. So we'll see lots and lots and lots of examples of that when we get to STL. It's one of the cooler things in C++ STL. And then the other thing that they have are adapters. There's all kinds of adapters. That's another pattern. So you'll see very quickly as we start talking about STL, patterns become relevant, and then we'll extend that as we get further on. Here are some of the key C++ features. Again, there's lots and lots of features. Key ones are data abstraction and encapsulation, which we'll talk about later, which talks about trying to hide implementation details from unsuspecting application developers or service developers like you. Classes, namespaces, those are good examples of abstractions in that space. Object-oriented programming, that's where C++ kind of got its start. It's evolved a lot since then to do other things. But some of the things you get with object-oriented programming are abstract base classes, inheritance, and dynamic binding. Those are really important concepts that have to do with how you can take something that exists and transparently extend it to do new things without breaking what you've already got. So it's a way of transparently adding capability to programs or frameworks. Generic programming with parameterized types, also known as templates, very important feature, really the mainstay of the C++ standard template library. More sophisticated error handling than just returning an error code. Exception handling, which is one of the more error-prone aspects of C++, not very well understood. We're going to spend time explaining this to you, so within a week or two, you'll understand this concept and will have no problem making it work when you need to have it work. And then something else that's kind of interesting that builds off of the exception handling implementation is something called runtime type identification, or RTTI. We're going to do it just a tiny bit in the class. RTTI is really more of an infrastructure kind of thing, and you use it when you need to be able to interrogate an object that's only exposed through its base class, but you want to find out what derived type it actually comes from. If that didn't make any sense, don't worry, we'll cover it in more detail later. Yeah?
Probably a silly question, but is the language still considered strongly typed if it supports runtime typing?
Sure, that's a great question. So the question had to do with strong type checking. So back when I first started learning to program, which was in the mid-'80s, strong typing was not as, it hadn't caught on the way it has now. So we used to joke and say, strong typing is for weak minds. Well, what people learned over time was that we all have weak minds from time to time, and nothing is more annoying than having a program that stops working for reasons having to do with violations of the type system or type safety. So modern languages, not all languages, but modern strongly typed languages like Java or C++, make it in such a way where violations of the type system, places where you're trying to use a square peg in a round hole, for an analogy, will show up either at compile time, which I think is what you're asking, or at runtime. And so it's perfectly acceptable to have a strongly typed language where you don't discover your type violations until the program runs. It's still strongly typed. It just is.
So it only refers to after compile time, its type doesn't change, but if it's, yeah.
So it's a fourfold chart. Let me draw you a picture. So you have the following. Let's see, typing, strong, weak, and let's call this time frame, static, dynamic. So some languages, like assembly language, are very weakly typed, and you're just out of luck. You can do all kinds of crazy things in assembly language that make no sense whatsoever, and you won't find out at compile time, and you won't find out at runtime. It'll just do strange things, right? So assembly language would be an example there. Other languages like Java and, well, some languages go much further than C++ and Java do with respect to dynamism, but they're still strongly typed. Right, so a lot of the more dynamically typed languages like Lisp or things along those lines, they would be up here. C++ and Java give you strong typing, but sometimes you have to decide at runtime whether something's strongly typed, so they would go there. Other languages will give you strong typing, but all the types have to be resolved at compile time, so you couldn't compile the program without knowing it was strongly typed. The problem is that those are often very limited. And so when you start having features like inheritance, where you actually are trying to intentionally allow runtime decisions about things, you don't want to limit it to only static typing. So C++ and Java are strongly typed, and they can detect those errors either at compile time and or at runtime. Now, C++ more than Java, if you really want to do bad things, you can do it. Right? There's almost always a way in C++ and C, if you really put your mind to it, to violate all the rules of type safety. Sometimes that's even a good idea. There are certain kinds of programs like debuggers where you need to be able to treat data in ways that doesn't necessarily respect the actual type it is, but want to access it in a more fundamental way. Java makes that much harder to do. In fact, it may be impossible without special access. Reflection gives you some ability to do that, but C++ basically lets you do it, but it's hard. You have to really put your mind to it. There's a famous quote by Bjorn Strustrup, the inventor of C++, who said, C++ makes it hard to shoot yourself in the foot, but when you do, you typically blow your leg off. So that's a good way to think about it. You can, if you put your mind to it, circumvent the type system, but it's hard. You can also do other sort of scurrilous things we'll talk about later with C++, and it's good for a parlor trick if you want to amuse people. So here are some strategies for learning C++. Don't try to swallow the 1,200-page book in one gulp. It's not going to be very tasty. You're going to choke on it, and you don't need it to understand all of those things. There's plenty of good stuff you can do with the basics we just talked about, and then learn things incrementally as you need them over time. There are C++ 11 features that I'm still in the process of understanding because they've added so much new stuff to the language. And I don't use all that stuff, so I don't need to know it. But there are people who do need to know it, and so it's very helpful to have it there. Learn C++ to become a better software developer. What that really is trying to say is C++ provides you with a lot of abstractions that you don't get in some languages. Again, if you're a Java programmer, then you already have a lot of these abstractions. But learn these abstractions to think more structured in the way you build software. And you can learn a lot from looking at other people who've done a good job, and we'll do a lot of that in this class. When we talk about learning from others, that, of course, suggests patterns and idioms, which are ways of documenting best practices that others have learned, often through the School of Hard Knocks, so that they're in a better position to be able to teach other people like you and me how to do things that we don't know yet. C++ supports a bunch of different programming styles. We're going to talk about some of them in a second. And do this gradually. So immerse yourself as you need it. You won't have to know all the C++ 11 features in order to do the first assignment. I guarantee that. OK, so that's the end of the first section. Just a quick overview of the background. What I'd like to do next is start walking through a series of different programming paradigms for building different kinds of software. And we're going to keep the example the same through all the different paradigms so that you don't have to worry about the example. The example you already know, it's a stack. And then we're going to look at different ways to build stacks, and we're going to compare and contrast the pros and cons of each of the approaches. And this will take you through about 40 years of software evolution in a couple of in a short period of time. So here's a very, very simple-minded solution to a stack. This is what you would do if you were sort of programming in C in an assembly language-like model. So we define ourselves a type def. As you can see, let me use my pointer here so you can see it. So type def int t, that just says anywhere I use t, it's really an int. Here we use a C. C is a macro to define max stack to be 100. In C++, we would do this, but we're pretending like we don't have those features. We now define ourselves a stack of 100 ints, but it's a little bit more abstract doing it this way. We define a top, set it to 0, and then we push and pop elements on and off of the stack. OK, so that's one way to implement a stack. What's wrong with this? Why would this not be, if you turned this solution in for your programming assignment, I'd give you a very low score. Why would that be? What would be the downside to it? Anybody want to hazard a guess? Yes, sir.
Well, I mean, it's got a very limited size. It's stuck at 100.
So we've fixed it to 100, and it's hard-coded. And if we want to make any changes to the size, we have to go back and change this and recompile the program. So expanding and contracting the stack is not going to be good. And it'll either be too big or too small, right? Yeah.
It won't detect overflow or underflow.
Right. So we push and pop things, and we're just assuming that somebody knows what they're doing. And if they don't, what'll happen if this happens to be the value of 100? What'll happen in that case? We're not quite sure what'll happen. Something bad will happen, hopefully. Actually, hopefully something bad will happen that we detect. Worse yet, what would probably happen, actually, if this was the value of 100, top would get set to whatever item was, because chances are that would occur next after stack in memory, right? So bad things will happen. This is not what we want to have happen. So good point. Range checking is not done. Anything else? Yeah.
It's not templatized.
It's not templatized, so we're stuck with an int. OK. Did you have anything else? Yeah.
It's not encapsulated, so it's really hard to put in a
Yeah, great point. So we've kind of programmed ourselves into a corner, right? If we want to make any changes, we have to go there and extract it out with an X-Acto knife, and we're stuck with it. Yeah?
You could have some exception handling.
So exception, it doesn't handle errors very well. That's absolutely right. A couple other things, just to make the point, there's only one stack. There's only one type of stack. That's the point about generics. And we're kind of polluting the namespace by using very generic names like top and stuff like that. So anyway, lots of problems with this particular thing. Most legacy software looks like this, okay? So the sad truth is a lot of people tend to write really crappy code. So if this was a class in 1970 or something like that, a great innovation around that time was people said, gosh, this exposing every last implementation detail is for the birds. Let's try to find a way to abstract a few things. So the first thing that they went after was abstracting representation of data. So here's what things would look like circa 1972 or something like that. So here what we have is a header file, stack.h, and in it we declare a set of methods, or functions actually. They're not methods, they're functions. So create, destroy, push, pop, top, is empty, is full. And those would go in a header file, and then this is what would be in the C++ file, or sorry, the implementation file. This is the implementation of those methods and our functions. As you can see here, what we have is we've got a bunch of private data, top, size, stack, all those things. They're all defined as static. And static is one of these really funky keywords in C and C++ and Java that means like 5 different things or so, depending on how you use it. In this context, it means these symbols do not get exported outside of the context of this module. So they're only visible to the implementation inside this .c file. So down here, we would implement create method, destroy, push, pop, top is empty, and so on. And I'm not going to go into the implementations in much detail, just to say that let's assume they're correct. Now we've defined an interface, and we've separated from the implementation. A lot of C code, a lot of legacy C code that's well written actually looks like this. Oh, quick question for those of you who are experienced. Why do I have to multiply size by size of t?
On older C systems, the size of the integer was not standardized. So it depends on, you don't know how many bytes the type takes up.
You're very close. You're definitely on the right track.
Well, if T can change its type, it will have different memory sizes. So you're going to need to increment by that memory size to get to the next one. Otherwise, you're not going to have enough space.
Right. So here's the way to think about this. When you call malloc, malloc is a legacy C function. Malloc dynamically allocates the requested number of bytes. So let's say we're going to create a stack of size 100, just to make it easy. So if you were to call malloc with just size, it would allocate 100 bytes. But the problem is we don't want 100 bytes, we want 100 t's, where t happens to be int, but it could be something else. It could be double, it could be float, it could be character, whatever we change it to. So if you don't multiply by size of t, then it'll give you that number of bytes, but it won't have scaled it by the size of each element. And this is a very common dumb mistake. I've done it myself before in C programs, to forget to do this. And so you end up with with much less than you asked for. So it's very confusing. Yeah.
If you're using a static keyword to make sure that the variables are hidden inside that single file, why is the underscore used afterwards?
The underscore is there just as a convention. So when you look at it, you know at a glance, oh, this is something that's an implementation thing. If you were doing programming in, I don't know, Android or something like that, they would say M. There are different ways to encode this type of thing, G or M or H or something like that. There are different ways to encode that kind of stuff. So the underscore doesn't change the visibility, it's just a mnemonic device to help the reader go, oh, this is meant to be internal. Okay, so here's how we might use this interface. So we've got some function foo, and we call push and pop and destroy. But there's all kinds of problems, right? So one problem we have here is that people have to remember to manually call create and destroy. And if you don't do that, then you can start out with your stack internally with nothing, with just a null pointer, which would be bad. There are ways around that, but they're awkward and costly in time and space. There's also only one type of stack and only one stack. So we have a stack of t's, but if we need 2 stacks, we're out of luck. We're also calling things very generic names, push, pop, top. If you write large software with millions of lines of code, you're inevitably going to run into a situation where that's going to be a problem, where other people will have called something pop or top as well. So you'll have what's called namespace pollution. And this solution is also not reentrant. If we were to have exception handling or signal handling or multi-threading and so on, we would end up with the various things corrupting the state of our stack if they occurred in different places at different times and different threads. So while data abstraction is certainly one step better than nothing, which is what we started with, it's by no means the most effective way to do things. Here's a slightly better way of doing this using C. So this will fix a couple of the problems. This will fix problems having to do with only having one of something. So now what we do is, instead of having just one, what we're going to do is make ourselves a stack, as you can see here. We make ourselves a stack data type. So this says typedef struct is called stack, and it's got top, size, and a pointer to a t. So this is basically taking all those things that used to be static inside of the file and making it a data structure. And then we pass the address of this thing to all the methods, or all the functions. So stack create, stack destroy, stack push, stack pop, blah, blah, blah. They're just exactly like they were before, except that they all take this extra parameter. So you can see the same signature that we had here, except they all take this new first parameter, which is the address of the object that they were manipulating. And the implementation would be essentially the same. So here's the way this would work. We could define ourselves multiple stacks, so that's a little better than what we saw before. But once again, we have to be careful because we're popping an empty stack. We forgot to create the stack. If we do some kind of assignment, we're in big trouble because we're copying pointers. That'll lead to disaster. And now we're destroying stacks that were never created in the first place. So this is very error-prone. There's still all kinds of limitations. So to summarize the problem with that approach, no guaranteed initialization, termination, assignment. Those things are still problems. Only one type of stack. A lot of function call overhead. Error handling is tedious and error-prone at best. And because this is C, you're really on the honor system. So if somebody wants to access these fields in this data type, nothing's going to stop them from doing that. There's no access control in a language like C. So all bets are off. If you really want to hide stuff, you have to do other things beyond what we've talked about here. Questions? Any questions about that? OK. So what's the solution? I'll cover this. I'll just start sketching the solution here because it's going to get us into more discussion than we have time for right now. But the solution, of course, is to use C++ and its class features. So you probably already know this stuff, so I can go through this fast. But we'll come back and talk about some of it in more detail later because it's really important. Stack is a class. Some of the methods here are so-called constructors and destructors and other kind of manager-like things. So we have a constructor that creates a stack of size. We have a copy constructor and an assignment operator. I'll talk more about that while we have two of them later. We have a destructor, which is automatically called to clear things up when these objects go away. We put stuff in the private part so that unless we stand on our head, we can't get access to them, which is good. It encapsulates the data more effectively. And then we have methods like push and pop and so on that are used to actually do the work. And here's the implementation of all this. Here's the constructor. I'm going to go through this pretty fast right now. We'll come back and talk about it later in more detail. We initialize things, make ourselves a new stack. Here's that's the default. That's the constructor that takes a size argument. Here's the so-called copy constructor. That's used to copy, make a new stack from an existing stack. We'll talk more about that in a minute. That's really important. Here's the assignment operator, which looks very much like the copy constructor, but it does something a little different we'll talk about. And then finally, we have the destructor. And the destructor is used to clean things up. OK, I'm going to go back and cover this in more detail later, probably on Monday. But a couple things to note for your first assignment, because some of you may want to get started on it. A very good rule of thumb, which we will enforce through comments initially and then later penalties if you don't follow them, is to do all the initialization of data members in the base member initialization section. So first of all, what's a data member? These things are data members. Top, size, stack, those are data members. And you should always initialize them in the base member initialization section. And I'll give you the rationale for that in more detail later. That's one thing to know. Second thing is, why is there a copy constructor that is distinct from the assignment operator, which we see over here? Does anybody know why that is? Yeah.
So the copy constructor, just a guess, the copy constructor actually needs to create a new stack, right? Whereas the assignment operator, if you have two stacks and you don't want to create a new one, you just want to copy the contents verbatim from one to the other. Use the assignment operator.
You're very, very close. Very close. Yeah.
It has its own default assignment operator that can lead to a thing requires.
That's why you need an assignment operator. That doesn't explain why we have an assignment operator that's different from the copy constructor.
The assignment operator needs to check for self-assignment.
The assignment operator definitely needs to check for self-assignment. Good A+ on that one. We'll come back to that. That's another frequently made mistake that you will all learn not to do. But the real reason, I don't want to belabor it too much because we're running out of time, the assignment operator has to clean up the left-hand side because an object already exists, whereas a copy constructor is creating the left-hand side in the first place. So there's no object that exists when you do the copy constructor, but when you do the assignment operator, there already is a left-hand side, and it has to be cleaned up. And we'll talk more about that. That is where a lot of the mysterious stuff that we're going to talk about with exception safety comes in, all the crazy things that are going on here. Then we have worker operations that do stuff. So here's what this looks like if we program it properly. We come in here, we make some stacks. Their constructors automatically initialize themselves. When they go out of scope, they're automatically deleted and cleaned up. You can't get to this point without having created this guy. If an exception is raised, for example, this won't ever happen. We check to see if it's not full. We push, we pop, et cetera, et cetera. If we try to access things that we don't have privilege to see, like the data members, the compiler will complain at compile time, statically doing the type checking to make sure we're not violating the type system. And if we do assignment, because we wrote an assignment operator, then we don't have any aliasing problems at all. So all kinds of goodness comes from doing things in this particular way. There are some problems, of course. So these are the pros. Those are the pros. Here are the cons. This error handling is obtrusive. Having to check everywhere, is the stack full? Is the stack empty? Is the stack full? That gets tedious. We only have one kind of stack. It's a stack of ints. And we still have this problem where everybody's making function calls, and those have extra overhead, which we did not incur with our really lame original version that had no abstraction whatsoever. So we had no abstraction, but we paid no abstraction penalty either. So what we're going to do, and we're not going to do it right now, but when we come back on Monday, we're going to go through and I'll talk about other C++ features, exception handling, parameterized types, various idioms of doing things properly, inline functions, etc., to fix all of these various problems that we have with these examples to this point. So this will really prepare you then for doing the first programming assignment in earnest. But for those of you who don't want to wait that long, and I would recommend that you don't wait that long because that won't give you very much time if you wait till Monday, let's go take a look at the first assignment. So we go to the website, which you should have the email that points you to. Go down to the bottom, programming assignment, C++ array class, and this explains what the requirements are for the assignment. And then it also tells you if you want to get the shells, then go over here, and you can take a look and get the shells. So these shells are basically little boilerplates that you use to start yourself off, so you don't have to figure out all the intricacies of getting started. And as you'll see, there's a makefile and some other things, and I'll explain what these things do, and there's a test program and so on and so forth. Now, if you're taking the class for grad credit, and those of you who are taking the class for grad credit probably hopefully know that you're doing that, there's a slightly different version of the assignment because you have to do a little bit more work because you're taking it for grad credit. If you're taking it for undergrad credit, which is probably the bulk of you, then there's another version. Typically, the way things work is that the version that the grad students implement, or the features the grad students implement in any given assignment, are then used for the undergrad version for the next assignment. So you'll learn pretty much the same things, just the grad students have a little bit more work to do up front. because the expectation is they have more experience. So those are the shells. A couple things to do between now and Monday. Get that VirtualBox, the thing installed, the VM, get that installed and working. Download the shells from here and at least get them to compile. And then start looking at the assignment, ask questions, post questions to Piazza. We're typically very responsive in getting you back feedback. If you're flustered and befuddled, go to office hours. There should be people tomorrow to help you out. And then on Monday, we'll go through the rest of the C++ overview slides, answer any questions about the assignment, get you ready for the quiz, and start on the next part of the course.